Okay, so today's lab is on thin layer chromatography. So what is chromatography? Well, chromatography is a purification technique. It's used to separate compounds, and it takes advantage of the fact that different compounds have different polarities, and it uses this difference in polarity to achieve the separation. Now, chromatography is made up of two different phases: a stationary phase, which is usually silica or alumina, which is very polar, and a mobile phase, which is a solvent that's less polar than the stationary phase, and your compound should be able to dissolve in it at least a little bit. And here we have pictures of a chromatography I did in the lab. On the left, you can see that this is actually not thin layer chromatography, this is the column chromatography. And what we see here is there's two compounds in this column. The top one is this bright yellow compound, while the bottom one is like a red-orange compound, and in between these two compounds, we see this nice white line, which is just the silica. And this shows that there's some very nice separation occurring in this column. And on the right side, we can see what these compounds look like once I got them out of the column, and they are very pure and very nice. Now, we know what chromatography is, but what is thin layer chromatography? Well, thin layer chromatography, as it's usually called TLC, it's just a type of chromatography. It's done on a smaller scale. So what it is the stationary phase, the silica or alumina, is actually deposited onto a piece of plastic. So they're like these little plastic rectangles that have stationary phase coated on top of them. And you can see an example of that here on the left. This is a TLC plate. And pretty much how they work is what you do is you get a pencil, and towards the bottom of the plate, you draw a straight line. And then you take the mixture that you want to analyze and you dilute it a bit. Then you take a capillary tube, like the one used in the melting point apparatus. Actually, they should be a little bit thinner than that. I actually have one right here. I don't know if you can see it. I'm holding up to the camera. It's just a thin capillary tube. And what you do is you take a little bit of that mixture with the capillary tube and you make a small spot on the TLC plate. You put a little TIG mark first so you know where you spot, and then you spot there on that mark. And you don't want to spot too much, because if the mark is too concentrated, what's going to happen when you develop your TLC is you're going to have a really broad band just run all the way from the bottom to the top. And that's not what you want. You don't want one big broad band. You want like defined small dots so you can see how many compounds are in there. So once you mark on the bottom of the plate, you put it in what's called a developing chamber. And this is just like a beaker with your mobile phase at the bottom. The mobile phase is also called the eluent. And you put in the beaker with the mobile phase in the bottom, and you cover the top of the beaker with like a piece of glass or something, because the mobile phase is usually very volatile and you don't want it to just all evaporate away. So, and also it's important not to put too much mobile phase in the beaker or the developing chamber, because if it reaches the area where you spotted the plates, it could wash off your compound off the TLC plate and you won't get any results. So you put your plate into the developing chamber, you put a watch glass or something over it so the solvent won't evaporate, and the solvent, the mobile phase, will start to travel up the TLC plate, and when it reaches your compound, it's going to begin to push them up towards the top of the plate. Now, what happens is the more polar compounds are strongly attracted to the polar stationary phase, which is the silica or alumina coating on the plastic of the TLC plate. And as a result, since it's so strongly attracted to the stationary phase, the solvent is going to have a hard time pushing it up towards the top. But the less polar compounds, they're not going to be as attracted to it. So it's going to be easier for them to get pushed up towards the top of the plate. So what we'll see usually with this type of chromatography, which is a normal phase, which is the only type of chromatography we'll talk about in this lab, is that the less polar compounds are going to be higher towards the top, while the more polar compounds can be found towards the bottom. And this is a TLC I did in the lab. You could see the plate is actually green because my compounds were colorless and I had to irradiate it with UV light. But you can see that most of my fractions here, there's two compounds present. The less polar one is towards the top and it's the nice big dark spot. And the more polar ones are towards the bottom. Those are the faint spots there. Now, right, it's also important that when you're developing your TLC plate, right, and you're watching your solvent travel up your plate, don't let it reach the top of the plate. You have to take it out before it reaches the top of the plate. You take a pencil and you trace out the solvent front, which is where the solvent ends. You draw a line across where the solvent stopped, and you keep that there because that's going to help you calculate your RF values. And RF values we'll talk about in this slide. So when do you use TLC? Well, what I usually use TLC for is just to analyze my reaction mixtures after either during the reaction or once it's completed, or if I even want to know how far along the reaction is. And like I told you a million times before, guys, when you do a reaction in real life, you're not just going to get your product, you're going to get your product, you're going to have some reactants, you're probably going to have some byproducts, some side products, etc. So what I do is to see what I have in my reaction mixture is I'll take a little bit of that reaction mixture, I'll dilute it a bit, I'll spot it on a TLC plate on one side, and then on the other side, I'll spot my reactants because I want to see if there's any reactants present in my reaction mixture. Because if I know for a fact that one of the reactants is a limiting reagent and I don't see it on the TLC plate once I develop it, I know my reaction is more or less complete. I can also tell how many impurities I have in the reaction mixture. You could also use TLC to tell how well your purification went. So for example, if you do an extraction, if you're trying to separate two compounds, you do an extraction and you collect your different fractions and you want to know, did I separate them completely, and you spot a TLC plate, you develop it, and if you see that there's only one dot there, then you only have one compound and it's pure. And if you see two dots, then you didn't quite separate them out completely. Or it could also be that your compounds have such similar polarity that they just overlap. That could also be an option. So we quantify the amount that the compound travels using RF values. And an RF value is just defined by the ratio of the distance from the baseline traveled by the solute. So the baseline is the line at the bottom that you drew where you spotted your compounds. So it's just the distance that your compound traveled from the baseline divided by the distance from the baseline traveled by the solvent front. So that's going to be the distance between where you spotted your compounds and where the solvent front stopped. And that's why you had to draw a line at the solvent front, like I told you in the last slide. And the RF values are always going to be less than 1, and they could be useful. So if you have compound X in your mixture, or if you believe to have compound X and you spot it and you develop it, and the literature read compound X has an RF of 0.5, and you have a dot with an RF of 0.5, then you know that there's a good chance you have compound X. So we know that this separation is being achieved through the difference in polarity, but the question is how exactly? What's going on? What's the driving force behind the separation? So let's take this theoretical situation and let's examine it. So let me explain this diagram that I drew in Microsoft Paint. Let's look at the leftmost quadrant. This black line is the stationary phase, the alumina, the silica on the plastic, and this blue square is the mobile phase. Now, I know that the mobile phase doesn't hover over the top of the stationary phase, but I'm using Microsoft Paint, so bear with me. So what we do is we spot this mixture, which is green, on the TLC plate, and we want to know how many compounds it's composed of. So we spot the mixture and we develop it, and the mobile phase begins to run up the column, and it begins to push the green dot, which is a mixture, up. And what we find is that the green dot is actually composed of two compounds, a blue compound and a yellow compound. And what we're going to see is that the blue compound is actually very polar in this situation. It's very polar, and it's going to establish an equilibrium between the polar stationary phase and the nonpolar mobile phase. Now, when the compound is attached to the stationary phase, it's not moving, it's staying still. It only moves when it's in the mobile phase. So since the blue compound is very polar, it's going to spend most of its time attached to the stationary phase, and it's not going to move. On the other hand, this yellow compound, it's not very polar, so it doesn't have a strong attraction towards the stationary phase, so it rather just hang out in the mobile phase. So this means that it's going to move much, much further than the blue compound, since it spends most of its time moving instead of staying still. And that's the driving force that achieves the separation. As we see here, as the TLC progresses, the distance between the compounds grows larger, and at the end, we have significant separation that we achieved. Now, this next slide shows what I just explained, but it shows it on a molecular level, which is very nice. So if we go here towards the left on A, I'll explain what this is. On the left-hand side of A, we see these silicon atoms. And they are arranged in a lattice of oxygens, and you see they also have these terminal hydroxyl groups. And these hydroxyl groups, they're very polar, they're capable of hydrogen bonding, so they're going to have strong interactions between other polar compounds. So if we take this benzyl alcohol and we spot it on TLC plate and we develop it, what we'll find is there's very strong intermolecular interactions between the benzyl alcohol and these hydroxyl groups, which are attached to the silica. And as a result, the compound is not going to spend a lot of time in the mobile phase. It's not going to move very far in the plate. It's just going to, for the most part, it might move a little bit. For the most part, it's just going to stay stuck in the same spot. If we go to slide B, we have a different compound, benzaldehyde. And benzaldehyde is moderately polar, so it's going to have some attraction towards the stationary phase, but it's also going to have some attraction towards the mobile phase. So it's going to move a little bit, not a whole lot. It's not going to go all the way to the top, but it'll move a bit. And in C, we see ethylbenzene. Now, ethylbenzene is pretty much nonpolar. It's going to have very minimal attraction to the solid phase. It'd rather hang out in the mobile phase, so it's going to move the highest in the TLC plate out of all of these because it's not attracted to the stationary phase, and it will not stay stationary for very long. And that is pretty much TLC. It's a very straightforward concept. And I know it seems like it's just a diagnostic tool. You can't really achieve any significant separation. You can't separate large amounts of product with TLC, but you can with other types of chromatography, and chromatography is a very powerful separation technique. I would say it's like the gold standard, honestly. It's really good at separating compounds. So that's pretty much it. These are my references: Chem Survival on YouTube, Chemistry Libre text website, and the laboratory manuals. So that's all for today, guys. Have a nice day.